Hey everybody, welcome at the final session at Pearson blog. Today we have Mateusz Półtorak, who recently was promoted to senior data scientist. He works at Pearson. Pearson is our platinum sponsor. Pearson was kind enough to support the conference for the 5th year. They also granted 2 awards for supporting grant for women in data science, for which we are deeply thankful for. Mateusz will talk about semantic information extraction. That's a part of unstructured data transformations block. And I've got a short information about Mateusz, whose great passion is modeling and mathematical approximation of complex mechanisms that rule our world. For over 2 years, his work has been focusing mainly on natural language processing. Currently, Mateusz focuses on merging 2 words, word of NLP, along with real-world use cases such as automatic assessment of English open-ended language tests. Privately, Mateusz worships all kinds of art. Mateusz, I'm not taking any of your time anymore. Good luck with the talk and have fun. Thanks.
Thanks. Hey, everyone. Thank you for the possibility to briefly talk about my work, which is also a big part of my personal interests. I'm really excited, so let's go. As you know, I'm Mateusz, and I am a part of the data science team in Pearson's AI learning capabilities. I work a lot on natural language processing domain. Therefore, today I would like to talk about text processing and semantic information extraction. In Pearson, as you probably know from Kacper's talk, we develop web and mobile platforms that help to learn English language. And while learning English, you have to train skills such as grammar, vocabulary, or pronunciation. But also there are other skills like comprehension and communication. And semantic information is a core of comprehension and communication. A lot of activities that you will take as an English learner are based on understanding and transferring knowledge. To give one example, I will use a task that is called describe a graph. In such a task, the learner has to analyze a graph and describe its content in a short response. This response is completely open-ended. If we want to automatically score that kind of responses, we need to ensure that our systems understand English language. Sometimes we need to infer very detailed information. I have another example for that. Let's suppose that you have a short story that is, yesterday I went with my sister to our local cinema. We bought a lot of popcorn and nachos. We wanted to see the next part of our favorite fantasy film. Unfortunately, at the beginning of the seance, a very loud fire alarm went off and everybody was forced to leave the cinema. As it turned out, the alarm sounded because someone was smoking a cigarette in the toilet. Now we will answer some questions. So the first one is, does this text mention a situation in a cinema? Yes, the answer is yes, it does. I put in bold part of the paragraph that shows it. So I went with my sister to our local cinema. This is the part. Then the next question, does the storyteller have siblings? Yes, she or he has, because I went with my sister. Then, does the storyteller like fantasy films? Also yes, she or he does, because of the part, our favorite fantasy film. Does the story have a happy ending? No, it hasn't. Unfortunately, everybody was forced to leave the cinema, that's the reason. And the last question, does the cinema sell cigarettes? we cannot answer to this question because there is no such an information in this paragraph. So now, big question. Can a machine answer those questions? Yes, it can. Furthermore, you are able to do it on your personal computer if you want. And today I want to give you some hints how to do that. In 2013, Google research team published Word2Vec. The Word2Vec algorithm uses a neural network model to learn word associations from a large corpus of text. I am not sure how many of you are familiar with the concept of training neural networks, and therefore I will talk about Word2Vec on a little bit higher level of abstraction. The main point is that you can convert words to their vector representations. And this is based on a large corpus of text, which in many cases is Wikipedia. I will name the word vectors also as word embeddings because they are embedded in a vector space. Word embeddings have n elements. In practice, the value of n is greater than 500. For the presentation, I will, of course, operate from much smaller values. Values of embedding elements are optimized in such a way that words which occur in the same neighborhood of other words have similar vectors. Now let's suppose that our word vectors are two-dimensional. It means that each of the vectors has two elements. Thanks to that, we can project them on a two-dimensional plane. I presented here a hypothetical distribution of a few given words. I've grouped them in pairs to show the concept. So you can see here that similar words are very close to themselves, such as apple and banana, or king and queen, or cooking and ate. Those words are very likely to occur in the same context, in the same neighborhood of other words. Therefore, the vectors are very similar. From now, I will be using an expression that words vector lies in an n-dimensional space. In this example, we have two-dimensional space, but normally it will be much bigger. To measure the value of word similarity, we can use cosine similarity metric. Cosine similarity is a dot product of two vectors divided by their magnitudes. Simple thing, I am sure you know this metric pretty well, so let's go forward. One of the most interesting properties of word vectors is the possibility to conduct arithmetical operations on them. If you take a vector of word king, subtract vector of man, and add vector of woman, you will end up with a vector that is very close to the vector of queen, which is very interesting. Thanks to that property, you can see that combination of multiple vectors can lead to new meaningful subspaces of a given vector space. That conclusion probably led you to a question. Can we represent a sentence by using multiple word vectors? The answer is yes. Let's suppose our sentence is Michael was too tired to tidy his room. To do that, we have to extract an average of words that belong to the sentence. So we tokenize the sentence into tokens. Michael was too tired to tidy, etc. Then we convert tokens to corresponding vectors. So every token has its own vector. Then we add the vectors together. We add it element-wise. So the first element from vector of Michael is added to the first element of vector walls, etc. And finally, we divide the results vector by number of tokens. Thanks to that, we received an embedding of the sentence. We can compare sentences the same way as we compare words, calculating cosine similarity between sentence embeddings. The use cases for that can be semantic search. Let's suppose that you want to find relevant content for your query. You're searching for a question and browser automatically shows you the most similar questions that were already asked in the past. Super useful on Stack Overflow, for example. In Pearson, we may like to check if a student's response is on topic. So if user writes an essay in English teaching tutor app, we check if the response is on topic. For both of those cases, I use, I name them paraphrase detection because those cases are based on comparison between sentence vectors. Of course, paraphrase detection term can be applied to many more methods, but this one that I present today is just one example. Paraphrase detection seems to be powerful, but in practice, it's not enough. Let's suppose that we want to compare two sentences. The first one is, the film received better ratings in Poland than in Germany. And the second one is opposite, the film received better ratings in Germany than in Poland. Now, let's think that if we calculate sentence embeddings for those two, we'll end up with the exact same vectors. Why is that? It's because those two sentences have exactly the same words. If we calculate average, it will be the same. How to overcome this problem? This problem is called a natural language inference. And one solution for this is based on supervised learning, which means because extracting word vectors is not supervised, you need a corpus of text, but you don't need to label it. Here, you need to label the data. The good news is that such a data exists already and is open sourced. The data set which we can use is called multi-genre natural language inference, MNLI. It consists of 433,000 of data rows that are human labeled. Every data row consists of a premise, a hypothesis, and a label. I will explain later what's that. We have three labels, negative, neutral, and positive, that are called contradiction, neutral, and entailment. So having two texts, we can treat one as a premise, and we can treat the second one as a hypothesis. So in the previous example, the film received better ratings in Germany than in Poland. Let's suppose this is hypothesis, and it will be a contradiction to the premise the film received better ratings in Poland than in Germany, because those are opposite. Going back to the first example, I've annotated our hypotheses with corresponding labels. Here we can see that the first three that were positive are labeled as entailment. The happy ending question hypothesis is labeled as contradiction. because the storyteller didn't manage to watch the movie. And we don't know if cinema sells cigarettes. There is no information about it, therefore it's neutral. Free label training, which is entailment neutral contradiction on MNLI dataset, is a perfect example of zero-shot learning. Zero-shot learning means that trained model is able to predict classes that are unknown. Here I've shown outputs of 2 neural networks. Let's suppose that we don't see the rest of the network. These are just the last layers, so don't care what is before that output layer. Normally, if you wanted to predict what is the topic that your text belongs to, you would train a classifier similar as the one on the left. It has output made of 10 classes. Each class corresponds to one topic. Topic can be movies, sports, animals, medicine, etc. In the natural language inference, you are independent on classes. Class name is another input to your model because class name is treated as a hypothesis. Example hypothesis can be, this text is about animals. This text is about movies. And premise will be the actual text. Hypothesis will be, this text is about industry, etc. Given such a hypothesis, network needs to infer if this is actually true, if this is contradiction, neutral, or entailment. That's how zero-shot learning works. So summary, word embeddings enable us to project word semantics into some n-dimensional vector space. Thanks to the arithmetical properties of word embeddings, we can construct sentence embeddings, and those are good to retrieve general domain of a phrase, but unable to infer exact meaning. Therefore, we can apply natural language inference, which is a good method to retrieve detailed meaning of a phrase. But at the same time, it's strongly data dependent and requires heavy computations to train a model. The last point, which is kind of subjective, but that's my opinion, that zero-shot learning is the future of NLP. I also put some useful sources into the presentation. I will share it after the talk, so you can read on the internet from the best sources that I know personally. Yeah, and that's all. Thank you for attention, and I'm waiting to answer all the questions.
Thanks, Mateusz. Thank you for your talk. This looks like you're really tackling advanced piece of data in your daily work at Pearson. So thanks for taking the time to talk about that. So let me just have a look at the questions. So do you calculate cosine metric on your own, or do you use any external packages? And maybe you can just also shed some light on what software do you typically use or recommend? What's your favorite?
Yes, so we mainly develop those models in Python. Therefore, packages that we use to calculate cosine similarities comes from scikit-learn and SciPy. But personally, I like cosine similarity is so simple metric to calculate that I like to define my own methods. So in that case, I would rather write something own that I am sure that I have tested it pretty well, and it won't change when new versions of packages are released.
Yeah, thanks. I would hope that some packages are reproducible and they don't break backward compatibility when they are released, but that's not always the case. So it's probably better to have your own implementation. And I think there's just another question again for the cosine similarity about the complexity. I can imagine that's very often used similarity measure in NLP. So maybe you can speak about some complexity. Is it ON squared or maybe that's smaller?
I would like if I told you right now that I know what's the exact complexity, so I can answer this question in the chat later.
Okay, maybe that wasn't the easiest one. You also said that some data sets or models are there on the internet already, and that you're using multi-general natural language interface. Are there any others that you might know or recommend? Are there any pros or cons? What did you actually? What was your decision to use this specific data set? And that's my question.
Yeah, great question. So in the sources on the last slide, I put also links to sentence BERT library that consists of many pre-trained models that are based on Siamese. I don't know how to say that in Polish. We call it Siamese networks that are trained mostly for the embedding extraction. In case of natural language inference, I believe that MNLI dataset is the strongest one that is actually open sourced, because you can, of course, you can browse models on. There is a site Hugging Face, which is a great package for Python NLP, and there is some kind of a hub where you can browse pre-trained models. I didn't see any other models that are great in natural language inference and are not trained on MNLI datasets. But we can search for it, sure. If you, on the last slide, there is also a link to the Hugging Face repository, so you can check for it.
Okay, thank you for that. And maybe one more question. So it looks like there's a lot of computations happening and a lot of data getting processed. Do you do that on your own machine? Do you have any cloud instances? How does it look like?
We have local machines, and we also use machines from AWS services. Recently, we received machines from other part of Pearson company from Boulder, and we received a machine with multiple NVIDIA Titan GPUs. So having such a computational power, you are able to train language model on the MNLE dataset. But you can, maybe you remember that on the very beginning, I said that you can infer that information even on your personal computer, even if you don't have GPU, because the inference time on those MNLE pre-trained models is actually pretty low. And if you want to do just inference, then you don't have to have big machines. If you want to train, then yes, because recently the paper about GPT-3, this is big language model created by OpenAI, if I remember well. It shows that the bigger the model is, the better knowledge and general understanding of language it has. And natural language inference works better on bigger models with much more parameters. Therefore, you have to train it on a very big model. But there is a model called BART. It's a follower of BERT model, which is a little bit more popular. And that BART model is probably the minimum that is able to get that general understanding of English.
Got it. Thanks, Mateusz. I know that the public speaking is always stressful, but it was a mixture of a webinar and a stream. I hope people can watch the video in their own time after it remains as a public video on our channel. So thanks again for joining and sharing your thoughts and best practices from Pearson. And again, Pearson is the platinum sponsor of our conference, and they were kind enough to support our causes financially. And this led to the supporting grant for women in data science, and we will announce the awardees of Women in Data Science grant awardees in 2 hours. So please join our channel at 1:45 UTC. And now we will have 15 minutes break, and later we will meet on another session. Thanks, Mateusz, for joining.
Thank you for a great time. Bye.
See ya.